You write a counter, two threads both increment at 1 million times, you expect 2 million, you get 1,372,481. You run it again, different number, you add a print statement to debug it. The bug disappears, you remove the print statement, it comes back, welcome to the race condition, one of the most frustrating classes of bugs in all of software engineering, non-deterministic, timing dependent. Invisible under a debugger. In this video we are going to build a complete mental model from the broken instruction sequence all the way to the production fix. Here is the scenario. Counter equals 0, thread A and thread B both execute counter ++ 1 million times. The expected result is 2 million. The actual result is somewhere between 1 million and 2 million and it changes every run. Something is silently discarding increments and you have no idea which ones or when. This is a race condition. The formal definition is that program output depends on the relative timing of concurrent operations. The name comes from logic gate design where two signals race to determine the output. Whoever arrives first wins. The problem is that in a multi-threaded program, the arrival order is controlled by the operating system scheduler, not by you. The root cause is that counter ++ is not one atomic operation. The CPU decomposes it into 3 separate machine instructions. First, a load, read the value of counter from memory into a CPU register. Second, an ADD, increment that register by 1. Third, a store, write the register value back to memory. These 3 steps are not protected. The operating system can interrupt a thread between any 2 of them and switch to another thread. Thread A loads counter as 0. Thread B loads counter as 0 before A has stored its result. Thread A adds 1 and stores 1. Thread B adds 1 and stores 1. Net result, counter equals 1 not 2. 1 complete cycle of work was lost. Overwritten by B storing a stale value, it loaded before a finished. There is a second, subtler problem beyond the 3-step interleave: cache visibility. Modern CPUs do not write directly to RAM on every store instruction. They write first to an L1 cache that is private to each core. The writes sit in that cache and get flushed to shared memory at a time the CPU decides, not when you decide. Thread A writes flag equals true to its L1 cache. Thread B, running on a different core, reads flag from its own L1 cache. From thread B's perspective, flag is still false. The write happened. The write is just invisible. Without explicit memory barriers or synchronization primitives, the CPU and the compiler are both free to reorder your reads and writes for performance. You can observe writes out of order or not at all. The classic fix is a mutex, mutual exclusion. You create a lock object. Before touching the counter, a thread calls lock. If another thread already holds the lock, the caller blocks and sleeps until the lock is released. Once it holds the lock, the thread executes its load, add, and store uninterrupted. Then it calls unlock. The next blocked thread wakes up and takes its turn. A mutex gives you 3 things: mutual exclusion, only one thread in the critical section at a time. Memory visibility, the unlock operation flushes all writes so the next thread sees them. Ordering, everything before unlock is visible to everything after lock. The cost is that threads block, the OS performs a context switch, and under high contention throughput can collapse. You also introduce deadlock risk if you ever nest 2 locks in the wrong order. For a simple counter you do not need a mutex at all, you need an atomic operation. In C++ that is atomic int. In Go it is sync/atomic. In Java it is atomic integer. Under the hood, the CPU emits a lock prefix on the XADD instruction. This locks the memory bus for the duration of the entire read modify write. No other core can touch that memory location between the load and the store. There is no interleave possible. The operation is indivisible by definition. Atomics are roughly 5 to 20 times slower than a plain increment, but roughly 100 times faster than a mutex on an uncontended path. They also provide memory visibility guarantees. The write is immediately visible to all cores. For a shared counter, flag, or pointer swap, atomics are almost always the right tool. Mutexes introduce a related hazard, deadlock. Thread A holds mutex 1 and waits for mutex 2. Thread B holds mutex 2 and waits for mutex 1. Neither thread can proceed. The program freezes silently. Deadlock requires 4 conditions to hold simultaneously. Mutual exclusion, only one thread holds a resource at a time. Hold and wait, a thread holds one lock while waiting for another. No preemption, the OS will not forcibly remove a lock from a thread. Circular wait, thread A waits on B and B waits on A. Break any one of those 4 conditions and deadlock becomes impossible. The most practical prevention strategy is lock ordering. Establish a global rule that lock 1 is always acquired before lock 2, everywhere in the codebase, no exceptions. Circular wait cannot form if everyone acquires locks in the same order. Race conditions are notoriously hard to find in testing because the bug window can be nanoseconds wide. The primary tool is thread sanitizer, built into Clang and GCC. Compile with the flag if sanitize equals thread. TSIN instruments every single memory access at compile time and detects data races, lock order inversions, and deadlocks with around 5 to 15 times runtime overhead. It tells you exactly which addresses raced, which threads were involved, and which locks were held. Run it in your CI pipeline on every pull request. The alternative for legacy binaries is Hellgrind under Valgrind, which requires no recompilation but runs 50 to 100 times slower. For races that are too rare for TSAN to catch in normal test runs, use stress testing. Loop the suspect code millions of times under maximum thread contention and add random sleeps between the load and store to artificially widen the race window. Beyond fixing individual races, the goal is to design systems where races cannot form in the first place. Immutability, an object that never mutates after creation, can be shared freely across threads with no locks at all. Thread confinement. Give each thread its own private data and eliminate sharing entirely. For a single shared counter or flag, use an atomic variable, not a mutex. For threads that need to exchange data, use a channel or queue and communicate by message passing rather than sharing memory. When you need concurrent reads but rare writes, a reader-writer lock allows many readers simultaneously with one exclusive writer. Copy on write lets readers share a snapshot while a writer creates a new copy and atomically swaps the pointer. Lock-free data structures built on compare and swap loops guarantee progress even if a thread is killed mid-operation. Let us put the complete picture together. Counter++ decomposes into load, add, and store. 2 threads interleave those 3 steps and 1 increment is lost. Your L1 cache holds the write invisibly from other cores until a barrier forces a flush. A mutex prevents interleaving and provides a memory barrier but introduces blocking and deadlock risk. Atomic variable uses a hardware bus lock to make the entire read-modify-write indivisible with no blocking. Deadlock forms when circular lock dependencies create a situation where no thread can proceed. Thread sanitizer catches races in CI before they reach production. And immutability, confinement, channels, and lock-free structures let you build systems where synchronization is rarely needed at all. Concurrent code is fast. Unsynchronized concurrent code is broken. The distance between those two states is a race condition. Race conditions are not exotic edge cases. They are the default outcome when you add threads without a synchronization strategy. The counterexample is simple, but the same pattern appears in every shared cache, every connection pool, every event listener list, and every lazy initialized singleton you have ever written. The good news is the tooling is excellent. Thread Sanitizer will find races you missed. Atomics and mutexes will fix them. And design patterns like immutability and message passing will stop you writing them in the first place. If this gave you a clearer picture of what is actually happening inside the CPU when threads collide, please subscribe. Thanks for watching.